Welcome to Cosmic Compass, the channel where we journey across the universe together, exploring planets, stars, and the mysteries of space. Here we don't just tell stories. We uncover the science and history that shape our cosmic neighbourhood. Today, we're setting our sights on a question that has fascinated scientists and storytellers alike. What happens when an asteroid threatens Earth, and how can we defend our planet from such a colossal impact? Imagine looking up at the night sky and knowing that one day a massive rock from space could change everything. What if an asteroid hundreds of meters wide were heading straight for Earth? Could we stop it, or would we face the same fate as the dinosaurs? These questions aren't just science fiction, they are part of a very real concern that has shaped the history of our planet. Today, let's explore asteroids, the dangers they pose, and how humanity is beginning to prepare for the ultimate test, defending Earth itself. Throughout Earth's history, asteroid impacts have shaped the world we live in. In the earliest days of the solar system, one colossal collision may have even created the Moon when a Mars-sized body called Theia struck the young Earth. Asteroids may also have delivered water to our planet, seeding the oceans we depend on today, but they have also brought destruction. 66 million years ago, the impact at Chelyabinsk left a crater more than 150 kilometers wide and triggered the extinction of the dinosaurs, wiping out around 76% of all species alive at the time. There is a clear pattern. The smaller the asteroid, the more frequently it collides with Earth. Large civilization-threatening impacts are rare, but history shows they are not impossible. Impacts actually happen far more often than we might think. Every year, Earth gains around 15,000 tons of material from space as meteors burn through our skies. Let's put that into perspective. Around 25 million meteors hit Earth's atmosphere every single day. Most are no bigger than grains of sand glowing briefly as shooting stars. On any given day, the largest meteor is likely no more than 40 centimeters across. In a year, perhaps one around 4 meters wide makes it through. And about once every century, a rock at least 20 meters across enters the atmosphere. Now consider this: every 2,000 years, a 100-meter asteroid is expected to hit Earth, causing devastation to entire regions. And once every several million years, a giant 10-kilometer asteroid appears, large enough to threaten civilizations. The good news is that these massive objects are easier to detect, and scientists believe we already know the orbits of nearly all asteroids of this size. But the smaller, harder to spot ones remain a serious threat. In 2013, people in the Russian city of Chelyabinsk witnessed firsthand how dangerous even a relatively small asteroid can be. A meteor, about 20 meters wide, exploded in the atmosphere, creating a shockwave that shattered windows across 6 cities. More than 1,500 people were injured by flying glass and debris. Now imagine if the same event had happened over a densely populated metropolis. The results would have been catastrophic. This is why monitoring the skies is so important. If we can detect asteroids early enough, we might be able to prevent the next disaster. In just the past 2 decades, astronomers have identified over 20,000 near-Earth asteroids that could one day pose a risk. Around 30 new ones are discovered every week. Most have harmless orbits, but what if one day we find one heading straight toward us? What could we do? This is where NASA's DART mission comes in, the double asteroid redirection test. Its purpose: to test whether we can actually change the course of an asteroid. The target is a system called Didymos, a near-Earth asteroid about 780 meters wide. Orbiting around it is a smaller moonlet named Dimorphos, roughly 160 meters across. Why target the moonlet? Because by hitting Dimorphos and slightly altering its orbit, scientists can measure the effect more easily than if they aimed directly at Didymos. The DART spacecraft itself is surprisingly small, about the size of a refrigerator. Its only main instrument is Draco, a high-resolution camera that helps with navigation and will capture the final moments before impact. Along for the ride is a tiny companion, an Italian CubeSat called LishaCube. Just 30 centimeters long, it will be released before impact to watch the collision unfold and send back images of the aftermath. Now here's the challenge. DART must guide itself completely autonomously. At such distances, communication delays mean there's no way to manually steer it at the last second. Using an onboard system called Smart Nav, the spacecraft will lock on to the tiny moonlet and direct itself in for the strike, or within the final hour before impact. When DART collides with Dimorphos at a speed of 6.6 kilometers per second, it will create a new crater and blast thousands of tons of rock into space. This impact will only nudge the moonlet's orbit by about 0.4 millimeters per second, but over weeks and months that small change adds up. And this is the key. If such a technique were ever applied to an earthbound asteroid years in advance, even a tiny nudge could mean the difference between collision and safety. Draco DART's onboard camera will send back its images in real time until the final moment of impact. LishaCube will then fly by to capture the plume of debris and study how material is ejected into space. This data is crucial. It will tell us how effective a kinetic impact is at shifting an asteroid's orbit, and it will reveal what happens to the surface and structure of these bodies when struck. But the story doesn't end with DART. The European Space Agency is preparing a follow-up mission called Hera, launching in 2024 and arriving by 2026. Hera will conduct a detailed investigation of the impact site. Think of DART as the punch and Hera as the detective arriving later to study the scene. It will map Dimorphos in detail, measuring the crater, the surface structure, and even probing the interior of the moonlet. From Earth, even our best telescopes can only see Didymos as a point of light. Hera will provide the close-up view we need, turning a bold experiment into a proven, repeatable technique for planetary defense. While we prepare to protect ourselves from asteroids, there's another side to the story. These bodies are not just threats, they are also opportunities. Asteroids are rich in metals and rare elements. Some companies are already looking to a future where asteroid mining could provide resources more sustainably than mining on Earth. What seems today like science fiction may, in the decades ahead, become reality. So what have we learned? Asteroids have shaped Earth's past, from delivering water to causing mass extinctions. They still pose a risk today, especially the smaller ones that are harder to detect. But for the first time in history, humanity is testing ways to fight back. The DART mission shows that even a small spacecraft can change the path of a celestial body. Hera will give us the data to make planetary defense a science, not just a theory. And beyond defense, asteroids may one day provide resources that fuel our future in space. As we watch the night sky, each shooting star reminds us of the millions of impacts happening above. Yet now, for the first time, we are no longer just observers of this cosmic drama. We are participants learning how to shape the outcome. So let's ask ourselves, if one day an asteroid truly comes for Earth, will we be ready? Thanks to missions like DART, the answer might finally be yes. Thank you for joining us on this cosmic journey. If you enjoyed exploring with us today, make sure to subscribe to Cosmic Compass for more stories and science from across the universe. Together we'll continue to ask big questions, unravel cosmic mysteries, and discover our place among the stars. Until next time, keep looking up, because the universe is full of wonders waiting to be found.